Right, higher order derivatives. So while it seems fairly obvious that we can perform mathematical operations repeatedly, we can multiply over and over, subtract over and over, we can do the same things for derivatives because differentiation is just another mathematical operator. So what I'm going to start with is finding just the derivative of this function. So first derivative, f prime of x, equals, so that's 3 times 4x to the third using the power rule, plus 2 times 1 plus 0, and again, I don't often write that, but for right now, we're just showing all of our work. And so I'm going to have 12x to the third plus 2. That's the first derivative. Now I can find the derivative of that derivative. I can do the whole process again. Okay? So the derivative of that derivative, I'm going to use the notation f double prime, because I've taken the derivative of the derivative, will be 12 times 3x squared plus 0 equals 36x squared. Almost ready. Okay, so some notations for the derivative. There are several shorthand notations. One of them is the f double prime notation, but after 2, maybe even 3 primes, it gets cumbersome to write lots of little tick marks like the 6th derivative. So we use parentheses and the number on the derivative up here. So even for 3, we can write the number up here. 3 primes is sometimes accepted, but more than that, we're going to have to write the number of the derivative. That's Newton's notation. Or there's also Leibniz's notation, which is if you're taking the derivative of the derivative, since the derivative notation is d dx of f, the d would be repeated across the numerator, so it's d squared f, and the whole dx gets repeated across the bottom, so d squared f dx squared. D squared f dx squared, same thing as the second derivative. Okay? And this notation can be used with multiple denominators. If you were in Calc 3, for example, you could have some ddx's and some ddy's, making that denominator have more than one variable. Okay? All right, last page, last example. When observations began at time 0, a cancerous culture had 1,200 cells and continued to grow according to this function. First, I want to compute the derivative, talk about its units, and what does it measure, why would this be important for researchers to know. Okay, so in part A, we're going to find its derivative. So it's constant 12,000 multiple of e to the t, so the derivative of e to the t is e to the t. So the derivative is the same thing as the original function in this case. What are the units associated with the derivative? So first of all, the units associated with the original function, p, is the number of cells measured in days. The derivative is, if I write next to it, this is, in other notation, Leibniz's notation, this is dp dt. And so its units are a rate of p units over t units. So the units are going to be in number of cells per day. Not just number of cells, which is the units for p, but number of cells per day. It's a slope measure, so it needs to have a ratio for its units. Okay. Why would this be important for researchers to know? So this is telling us how many cells, cancer cells, the culture is increasing by per day. Okay. So it tells us the rate of growth. So they can use that rate of growth to predict what's going to happen in the future from that cancerous culture. All right, so part B, on the interval 0 to 4, where is p prime of t the greatest? Where is it the least? B here. So I know what e to the t looks like. You can use your calculator to graph it if you need to, but I know that any e to the t function looks roughly like this right here, and if it's 12,000 times e to the t, it just means my y-intercept right there is at 1,200, I meant to say. So this is a graph for, remember that they're equal, so this could be the graph of p of t, or p prime of t. In this case, I want it to be a p prime of t because I want to find when p prime of t is the greatest. Okay. And again, because I know the shape of this graph, I know that it's going to be greatest because this function is always increasing, right? Always increasing. So I know that it's going to be the greatest at 4, and the least at 0. Okay, so I can conclude, because of the shape of this graph, that P prime of t is greatest at t equals 4 and least at t equals 0 on the interval 0 to 4. And that's because the P of t function, exponential functions, are always either increasing or decreasing. With a positive coefficient, it's always increasing. All right, last part, part C. Does the curve, P prime of t, ever have a horizontal tangent line? Well, it does. It has a horizontal tangent line over here, right? The horizontal tangent line would be y equals 0, and it reaches y equals 0, the limit would be as x approaches negative infinity. The limit as x approaches negative infinity of P prime of t is 0. So that's the limit for the horizontal asymptote. Okay? So what does this mean about the derivative? Prove this algebraically and verify graphically. Okay? So I looked at it graphically. Let's talk about what it means first, and we'll prove the limit algebraically later on. So what this means is that when the cell perhaps first developed, this is before it's been studied, at t equals 0, there are already, if you plug 0 into this function, there are already 1,200 cancer cells at t equals 0. So there were cells growing before the study happened. As time went further and further backwards, so as time goes backwards, so back in the patient's history or back in the culture's history, backwards, there were fewer and fewer cells. Never actually 0 cells though, right? The limit is 0, which means that there were always some cells. Okay? There were always some cells. But that production is rapidly increasing. So cancerous production is exponentially increasing. Okay. Last, just a review of limits to prove that limit algebraically. We're going to do the limit as x approaches negative infinity of the 12,000 e to the t. That would be 12,000 e to the negative infinity. A negative puts that in the denominator, so 12,000 over e to the infinity, or 12, I keep saying 12,000, I apologize, I mean to be saying 1,200. 1,200 over infinite, because e to the infinite goes infinite. It doesn't matter what the numerator is. If your denominator goes infinite, it goes to 0, as long as your top is finite. So again, that's just the analytic way of proving what we saw graphically.